All right, so this is a fast review of what we got. Let me check to see if we can. Zoom changes the way they do stuff every single week. All right, almost. Okay, can you guys see the PowerPoint? Yes or no?
Yes.
Oh, so if I can just switch, it just switches automatically. That's weird. I like it. Makes it easier. All right, so
Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current.
All right, guys, conceptually, this is the way it is, but mathematically, how you represent this. So the mathematical representation of this is what we will be focusing on. Okay. Yeah, so I was right here, so you guys can see this, right? Mathematical representation of this. All right, there's a couple of ways of doing it. I'm gonna go easy on you guys today mathematically. Okay, so we will. Okay, cool. We almost made some progress here. All right, guys, feast your eyes on this one. The mathematical representation of Ørsted's 1820 discovery was done by two Frenchmen, Biot and Savard, and it looks kind of nasty. Okay, how it is done is a discussion that we will have tomorrow. Okay, I don't want to start at this point. Mathematically, it's not bad, except for you guys, it's a little bit too much work. You guys, most of you guys have take Calc 1, Calc 2. This requires Calc 3, and then eventually you will come up with this formula. Okay, so that's the formula that we will focus on. That is the formula that we will focus on. All right, so. All right, so here's Ørsted's discovery. Current is going in the opposite direction. And the magnetic field is simply going to wrap itself around the current wire. And that's what it does. So here's the magnetic field. It's going to be a certain radial distance away from it. So the strength of this magnetic field is going to be represented. It's going to depend on the current. And it's going to be inversely proportional to the radial distance. All right, so this is a constant. This is a constant. These are your variables. All right, the larger the current is, stronger the magnetic field is going to be. Further away you are, weaker the magnetic field is going to be. All right, so this is one of the formulas that we will focus on. Just ignore the derivation of it for now. All right. The second formula that I'm going to present, what if you have a current loop just like that? All right, so the current loop is going to generate a magnetic field around it. And I will be interested in the magnetic field, the total magnetic field pointing in this direction right at the center. All right, so that's the magnetic field right at the center that we're looking at. Okay, this is, so pull this to the side. It's gonna have a formula that looks exactly like this formula, except I'm gonna send this into a black hole. It's just gonna vanish. All right, so. All right, so the formula is gonna look like that. All right, so this one is a current loop. This one is a current wire. All right, so, okay, so these are the basic equations. Okay, so let me come up with one more. This time, let's have a loop, a wire. All right, so, and then just close it just like that. It's gonna have a number of turns, has a certain length, and it's got a number of turns. All right, so L is the length of the loop, N is the number of turns. Okay, so, and then let's just get the current moving. All right, let me just change color here. All right, so we have current going up in that direction. And then, so, which means that there's magnetic field is, all right, it's gonna go into the page. All right, so it's gonna do this. Okay, so that's your B. All right, so the strength of the magnetic field in this case is going to be denoted just like that. Okay, lowercase n is the number of turns per unit length. And this thing is called a solenoid. Okay, so which formula? These are the three formulas that I want you to know. Okay, so this one is a representation of what Ørsted discovered. All right, so the current causing magnetism is this. All right, and somehow magically, if you have a loop, current loop, it causes magnetism. All right, so that's the formula that we use for that. And if you have a solenoid, this is the formula that we will get to use for that one. All right, so what is the formula representing the strength of the relationship between what's the formula representing the relationship between the strength of the magnetic field due to a current? In this case, the formula that we will get to use is this one. All right, so the current is going up, and it's causing a magnetic field. All right, so magically somebody came up with this formula. So the question is how, and that's the sort of stuff you will sweat through on Sunday. All right, because conceptual stuff is important, but the math, you need to be able to back it up using math. All right, so what happens to the strength of the magnetic field? If the current increases, you increase the current, the strength of the magnetic field is going to go up. All right, so you get this direct correlation. So what happens to the strength of the magnetic field as the radial distance increases? So the radial distance increases, the strength of the magnetic field is going to diminish. So we got the inverse relationship. All right, so 37, 38. Okay, we'll move on to that one. Let's move on to 40. So what happens to the strength of the magnetic field within a solenoid is the number of turns increased. Okay, it says within a solenoid, something we will emphasize later, not right now. What I'm going to do is I'm going to just write down the formula. The formula regarding the solenoid is this. All right, so N mu naught times I. All right, so the question is, what is mu naught? No one asked that question. It's just a constant. Okay, it showed up here. Once again, no one asked that question either. Okay, so what is mu naught? Okay, guys, mu naught is the same as epsilon naught. All right, so it is the magnetic representation of the electrostatic factor. All right, so this is known as the space permittivity constant, and this is known as the space permeability constant. All right, so this sets the limit in terms of how fast the electric field can travel inside a vacuum. This is also going to set how fast the magnetic field is going to travel inside a vacuum. All right, so this is going to put the brakes on regarding the speed of the magnetic interaction. This is going to put the speed on regarding the interaction through the electric field. All right, so whatever that is, we'll get back to it shortly. Just understand that these are just constants. All right, so what's the formula representing the strength of the magnetic field within a solenoid? All right, so we got that. So it depends on the current. Stronger the current is, the stronger the magnetic field. Larger the number of turns per unit length, stronger the magnetic field. That's it. So once again, the solenoid looks like that. All right, so it's a multiple current loop. All right, so you have number of turns per unit length. And we are interested in the strength of the magnetic field right in the middle. All right, so if the current is moving in this direction. All right, so what happens to the strength of the magnetic field is you increase the number of turns. All right, so when you increase the number of turns, number of turns goes up, strength of the magnetic field is going to go up. All right, so the number of turns goes up, the number of turns per unit length goes up, the strength of the magnetic field goes up. Okay, so what is the formula representing this? What is the formula representing the strength of the magnetic field at the center of a circle loop? All right, so circular loop. I don't know that color. All right, so this is our circle loop. And we are interested in the strength of the magnetic field right at the center. All right, B. And that's it. Okay, so once again, two interpretations. Stronger the current is, stronger the magnetic field. All right, so R is, let's indicate what R is. That's the radius. Further away you get, the weaker the magnetic field becomes. Okay. Okay, so 37 and 38 is where we will start right after the break. So I'll take a break for 10, go back in 10, and we'll take it from there. All right, guys, let's express this mathematically. So the currents are moving in the same direction. Wires will be attracted. They're moving in opposite directions. They will be repelled. So we gotta come up with a mathematical expression. Current is coming out of the page. Okay, I'm gonna make this I1. Just for the hell of it, let's assume that we got a second wire. It's gonna be I2. Okay, let me just put them nearby. Okay, so the current wire, current due to the first one is going to create a magnetic field going around just like that. And the strength of the magnetic field right at this point is going to be due to the first wire divided by 2 pi r. R is the radial distance between these two wires. It's the same as this distance. Okay. All right, so what's going to happen to this wire? It's going to experience a force to the left. It's going to experience a magnetic force to the left. The magnetic force that it's going to experience to the left is going to depend on the length of the wire, strength of the magnetic field, times the angle between the direction of the magnetic field and the direction of the current. Okay, so I'm going to change the terminology just a little bit. Okay, so this is the force acting on the second wire due to the first wire. And this is the strength of the magnetic field. Okay, so the angle is between the magnetic field and the direction of the current. So this is going to be 90 degrees. All right, so sine of 90 is going to be 1. And that's it. Okay, now we get an expression for the force acting on the second wire due to the magnetic field generated by the first one. It's going to be the current of the second wire. All right, so the length. And this is the magnetic field due to the first wire divided by 2 pi r. Okay, so I'm just going to clean this up. You got your mu naught. And r is going to be the separation distance between these two.